Hello? Hello, hello? Hello? Hello, hello? Sick. Hello? Let's put this bloke right in the middle of the screen here. That's not right. Okay. Bag of chips. Alright. Let's get ready to learn. Where should I put Joel? I'm getting water. Welcome. I guess this is for the VOD. No viewers. Alright. So tonight, I'm going to be eating chips while teaching you guys about TCP, UDP, a little bit about how we do checksums with TCP and UDP. We'll probably take a little peeky poo at some bitwise operators, maybe. It's gonna be chill, and we're gonna eat a bag of chips. I'm gonna eat a bag of chips. Because it's 7:51. I haven't even eaten the past hour, but as of 5:30 p.m. I've eaten 270 grams of protein already, but almost less than half my carbs and not enough fats. So what do you do when you need a ton of fats and carbs, but absolutely zero protein? Eat chips. Or you fail to eat chips. So, I'm gonna shrink myself to an appropriate size. I guess I'll just start with my obsidian. Yeah, we'll put obsidian there. We'll put helium. Oh my god, it's hard with one hand. I'm getting chips on the computer, but I put that there. Okay. Close this up. So we've got Beej's book on the left there, and my notes on the right. These notes are basically what's in Beej's book here, and I'm probably not going to be scrolling too attentively through my notes because I'm eating chips. Yeah. But in the last stream, I explained the word server project, where we had to write a client that would ask a word server for a stream of TCP packets that contained random words, and we had to like just parse those out and put them into console. In the context of that project, in the context of like where you're at in Beej's guide when you're doing that project, it's not actually framed as TCP. You're doing TCP without knowing it at that point. So I guess that's where we'll start explaining, even though UDP is probably a little simpler to explain. It almost is. It's neat to see what UDP does in contrast to TCP, as opposed to like TCP, which is so much more complicated. So yeah, TCP. That's the Transmission Control Protocol. My mouth gets dry when I speak normally. I wonder how these full salt chips are gonna. So, TCP sits in the transport layer when we're thinking about the OSI network layer model. So that's the transport layer is beneath the application layer. Like earlier in Beej's guide, we were learning about HTTP, which was an example of an application layer protocol, and that really has to do with user data, application data itself. Whereas we're one layer lower in that model now at the transport layer, which is primarily responsible for the integrity and data integrity and packet splitting, and reassembling packets. And TCP and UDP aren't the only transport layer protocols, but they're like, I don't have the actual numbers, but between the two of them, they're probably like 90+% of all transport layer like it's ubiquitous. These are what we need to learn, I guess, before we do other stuff. I'm just trying to think. So yeah, we said it's a lower layer, one layer lower in the transport layer. But with the OSI network model, sort of a little bit counterintuitively, it's important to remember that like as you go down, we sort of think of it as going down the stack, and as we're going down the stack, we're adding headers. So like the application layer has, if you think of like an HTTP request that has like a body and a header, once we go down to the transport layer, we're wrapping that application layer's data. We're putting a TCP header on that data. And then when we go down to the IP layer, we're adding an IP header and a footer, or maybe that's Ethernet, to the transport layer data. So I think it's called encapsulation as you go down and demultiplexing as you go up, but that could be wrong. I don't know. So what do we use TCP for? This is the protocol we use when we're trying to send data from one machine somewhere to another, where we're kind of trying to simulate like a circuit switch network, even though we're obviously on a packet switched network. So if you circuit switch network refers to back in the day, when you had to like talk to someone, you would like if you could run a wire from here to the other room and pass like a current along that that like you could encode like Morse code or even voice data later on this wire, somehow like turn the information into current and pass it over the wire, and the host could turn that back into like audible, whatever, whether it's Morse code or voice. But to facilitate larger and larger networks, like how do you, right? How would I send that to someone in the next house or across the sea or whatever? So they had these centers where you would call this, I don't forget what it was called, like a patch, like a switch center or whatever, like where you're calling them in. They're physically configuring wires on like a patch board such that there's a physical link between you and the hoping, to be a receiver so they can hear your stuff. Anyways, that's what we're trying to simulate here. We're on a packet switch network, right? We're sending packets but we're trying to simulate it as if there's this like a tunnel between us and a user or a receiver or a server or whatever. So TCP. Let's actually get into it. So this is a protocol for handling that assurance of getting stuff somewhere, and with all the assurances that transport layer stuff tries to do, where we're concerned with the assurance that whatever we send gets there in order. If stuff gets broken up, that we can reassemble it back in order. If it comes if packets become out of sequence for some reason, they become in order. And for providing flow control between the sender and the receiver, and for providing congestion control so that the sender can have an estimation about how much congestion there is on the network. We'll explain flow and congestion control better later. So yeah, the goals of TCP right now, this is all kind of just like random sounding, but it makes more sense the more I talk about it. So how does TCP work? We make a connection, we send data, and we close the connection. That's nifty. That sounds like it's a given, but you might reflect and realize that it's maybe not a given that there's this actual persistent connection between two devices. What if I have a client host machine that wants to send data to a certain address and port, but not necessarily keep a persistent connection open? It just sends out the packet and that's it. So we'll learn about that later, but this is with TCP we're talking about forming a connection, keeping that connection open for the duration of sending packets to and maybe fro, whatever, and then closing it when it's time, when appropriate. And if you think of the word server program or the Better Server project, part of the speech guide, you can see why those were TCP, right? We were using the socket library. You would bind to like a port and address, and you'd spin up that second socket. That's my cat. To send information back and forth on while you kept that other socket open to receive further potential connections from other clients. So that's TCP. That's what that. Whoa. I've never heard my cat make that sound. Papa? Are you good? Oh, her nails caught in her tail. Are you alright? Oh, I lied. She's fine. What a tool. Okay. So, to be a little more specific about this making the connection portion, this first step, we first need to talk about packet types. Packet types are, there are tons of different ones, but the ones we need to understand are SYN, SYN-ACK, ACK, and FIN. So and this is, we introduced these so that we can talk about this three-way handshake, which is how we form the connection. The three-way handshake is this famous idea, and like with TCP, where what we're doing is the client says, hey, or not necessarily the client, just the, I guess sender and receiver is more accurate, but sender wants to send some stuff. The receiver acknowledges that the sender wants to send some stuff. The sender acknowledges that the receiver has acknowledged the sender wants to send some stuff, and then sends stuff. And then there's, what do you do when it's closing too? So the three-way handshake, the client sends a SYN packet for the server or receiver. The server replies with a SYN-ACK packet, SYN-ACK. The client responds with an ACK packet. Then, so everyone knows, both parties concerned are they're in agreement that they want to send stuff or receive back and forth. And if there's not a reasonable, if there's no response within a reasonable amount of time for any of these packets during the three-way handshake, that packet is resent. So how does the data get actually transmitted? TCP takes a stream of data and splits it into chunks, where each chunk gets a TCP header attached to it, which is then sent down to the IP layer for delivery. So this is what we were discussing earlier. You might have some application data from HTTP or FTP or SMTP, any of these protocols, and you are putting a TCP header on it and then passing that down to the IP layer, which handles the routing of your stuff from your machine over the network to some router somewhere to some other network to some machine, whatever. So you can access your agentic whatnot. Very good chips. I was just talking yesterday how I think classic or like plain chips fucking suck, but I was in fact eating a no-name brand, which are like, if these are regular amount of salt, those are like double, triple amount for no reason. So it's just a bit much. Okay. So we've got some application layer data. We put a TCP header on it, right? Send it down to the IP layer. This header plus chunk of data is this TCP packet we're talking about, and TCP packets are more accurately referred to as segments. So TCP expects an ACK in return when a segment is sent, asterisk. But if it doesn't get an ACK back, it assumes something is wrong and resends a segment which didn't get an ACK. And these segments are numbered. I said an asterisk, we'll get back to that. Segments are numbered. They have like a sequence number, right? So that even if I send segments 1, 2, 3, and I'm the sender and the receiver gets 1, then 3, then 2, it's no issue on the receiver side. They can reassemble those segments and take the TCP header off and get access to the data in order, you know what I mean? So, and when a side wants to close a connection, it sends a FIN packet. The remote side typically responds with an ACK and a FIN of its own. The local side would then complete the hang up with an ACK of its own. So it's like a reverse three-way handshake again. And then some OSs support a reset code thing, which is if a connection is closed with unread data sent, I get like still data to send, it sends back on a reset to indicate that if that socket were to be opened up again. So that's good. We've talked about the handshake and whatever, but again, we're doing all this TCP stuff, not just because we like handshakes, but the data integrity part. So we're going to talk about how we can assure that by using TCP. So it can arrive out of order. Like what are the bad things that can happen to data? It can arrive out of order. It can be corrupted. Corrupted means what you think it means. There could be for a few reasons. It could be duplicated, or it could just not arrive at all. How do we mitigate these things? So packet ordering, we've talked a bit about this already, but the sequence numbers allow the receivers. If you get a bunch of TCP packets, you can handle them if they're out of order, if you have duplicates. If a particular segment is missing, you can ask for it by repeatedly ACKing the previous one, the previous sequence number, which will make the sender resend that one. And if the sender doesn't get an ACK for a particular segment for some time, it might just retransmit it itself. It might just take the initiative on the assumption that that packet might have been lost, that segment might have been lost. In which case, and that is increasingly pessimistic, which means that there's like ramping up timeout time between these auto retransmissions, so that, yeah, you're not like just flooding. That's probably for congestion control, maybe, or avoidance. Any viewers? Not one. Oh. Jeez Louise. Too many browsers. I have 3 browsers. One for work, one for personal coding, and one for YouTube and email, which is also kind of my work one. And my work one. Okay. So that's the ordering, but some of the more interesting stuff now. Error detection. So we said, what are the bad things that can happen? They're out of order or duplicated, but now there's this idea of corrupted data. So how can we prevent corruption? I don't know if you can. That's probably out of your control. What you can do is detect errors and react accordingly. So what this is done with checksums, which are a concept from a few disciplines in like computer science. But this is an algorithm used to take some data. It's not entirely unlike hashing in that you are taking something and computing like a real integer value to represent that, so that you can compute it again later on to see if they match. And they match because you are sort of deterministically generating some sort of number based on some data, and if that data is the same from across 2 points in time, then the checksum will be the same. Or so if the checksum is the same, the data is the same. What this actually means in this context is that when the sender is about to send its header plus chunk of data, it computes the checksum on its side and puts that right into the TCP header. And the receiver takes a look at this segment it's received. It looks at what does the client, or what does the sender say the checksum should be, and then it computes the checksum for what it actually got, the header it actually got, the data it actually got, and it compares that checksum to the one the sender put into its header. And if they match, the data arrived in one piece, or no, that's a bad way of putting that, because the data arrived uncorrupted. If they differ, you just discard the data, and you have to time out and retransmit or ask for it again. Yeah. And it's a 16-bit number, which I'll probably explain better once I get to the checksum part. Okay. Oh. So that's error detection and ordering. What about flow control? The next two are flow control, congestion control. And these are two problems we're trying to address with TCP. Starting with flow control. This relates to the sort of capacities and of the sender and the receiver, and make, like, when we're talking about TCP and all, the way I've been explaining it, I'm really making it sound like you've got like a computer and like you know, the state diagram, or like the flow chart or whatever, right? These are like, you're thinking of arrows between these two things, but keep in mind this is all happening on like the internet, the public internet, where there are like over 1,000 sub networks all put together, and each of those networks has hundreds of little networks inside it, on which it is, you know, your home network whose Wi-Fi you're connected to on your device, and you're asking for some social media data to be shown to you on your device, and that data is on a server on some other network in some other country, blah blah blah. So we're putting on our realistic pants a bit when we're talking about flow control and congestion control here, in that this is beyond just the sort of little boxes with arrows between them. Anyways, that's enough of that. Shut up. Flow control. This is how do two devices tell each other how to slow down or not, based on their own capacities to receive as much as is being sent to them. The analogy Beej gives in his book is that if you're on the phone with someone and they're just like barking at you and they're going at 1,000 words per second, this is flow control, is you being demanding. You're the receiver. You're demanding them to, like, you gotta slow down. I can't understand what you're saying. I'm missing everything you're saying. So how do we do this? Well, the simplest way, most like surefire way you could do flow control is that you wait for an acknowledgement on every segment. If you're a sender, you send a segment, and the simplest way to do this would be for TCP to enforce the fact that every time a segment's sent, the sender has to receive an ACK from the receiver, and then only then can it send another one. Now, then this would allow the receiver to delay the ACK if it needs the sender to slow down by just withholding that ACK. This is obviously would be cool, but this is just way too slow. And in reality, what TCP actually does and sort of has tolerance for is sending numerous segments at a time without actually receiving an ACK for that first one. So you can send a couple and not have actually been told that first one you sent a little bit ago even got there yet. So this is, yeah, so, and that behavior comes from this insight that typically under average conditions, networks should be reliable enough for the sender to push out multiple segments without waiting for a response. So that's a cool realization. It's nifty and it affords us to send things faster. But we need to acknowledge the risk we've created by doing that, which is we might send more packets than the receiver can receive. This might be the network interface card of the receiver just isn't beefy enough to. That's actually kind of unrealistic, but that is possible. Anyways, so TCP, this introduces this concept of a sliding window, which is a value that yet another thing we are putting in this TCP header. So this header is getting quite big, lots of different little fields in it. And this is the number of bytes the number of bytes the sender is allowed to send without receiving an ACK from the receiver. The number of bytes the receiver is willing to receive. The sender must not send more than this without getting an ACK from the receiver. So that ACK will contain new window information. So this can get changed back and forth as needed, as the receiver says to slow down or to speed up. So the receiver can tell the sender, once you've sent X bytes, you have to wait for an ACK from me, which will also tell you how many more to send. And critically, this is a byte count, not strictly a segment count. So you can send multiple segments without receiving an ACK from a receiver if the total number of bytes in those. Dude, my cat's drinking my water. You're grotesque. I'll be back. What the hell, man? Whatever. It's so not cool. Okay, so that's flow control. What about congestion control? Now this is a tricky one. This is a tricky problem. We've addressed ordering. We've addressed the integrity, like the assessing corruption or not, or if it was corrupted or not. And we've even addressed flow control. How do we tell the sender to slow down? But there's this other nefarious problem that can occur, which is and this has nothing to do, strictly, it's possible that this has nothing to do with the way you're sending stuff or how they're receiving their stuff. And this is about the behavior of networks as a whole, which is that, like, if the router servicing, like, we're only on the transport layer right now, but if you go down to the IP layer, the router handling all that stuff might be totally overwhelmed for whatever reason. It could be, might be servicing your stuff along with a whole bunch of other crap. In which case, like flow control can't help us here. Because the receiver isn't received. So when a router gets overwhelmed, it starts dropping packets, and so the receiver is not even getting these packets. So the receiver can't even tell the sender to slow it down, and therefore not worsen the situation. So we need to kind of have like a heuristic for estimating this congestion, and try to avoid it, and like handle it as best as we can as partial contributors to the problem, potentially. They work together. Flow control and congestion control work together. So there's a flow control limit, and then there's the congestion limit. The flow control limit's like the sliding window we talked about, but there's also a number for this congestion limit, and the sender must like obey the limit, whichever of these limits is lower. So you cannot have more unacked packets out there than this limit. If it does, you have to stop and wait for some acts. So, how do we do that? Oh yeah, the last little way to think about this is if you're a sender machine, you send packets out. The congestion increases. Maybe not in a bad way, but just like there is more packets out on the network right now. When a sender receives an ACK from, because the receiver sent an ACK back on receipt of that segment, network congestion has decreased because there's one less packet out on the network right this second. So we're trying to push the limits as much as we can about how fast we can go without causing serious congestion. And this is done with two algorithms that work together, but happen sort of one after the other, and then flipped between them. So the first one is slow start, and this is an exponential algorithm where you first, as a sender, so say you've just opened up the connection. The sender doesn't know how congested the network is yet. It has no heuristic for finding this out without sending out a packet. So you just assume that there's like a high level of congestion on the network, and so you just send like a tiny little bit, a tiny bit of, like just a couple segments, or it might just be one. I don't know. Yeah, so you assume high congestion. You assume an initial really small window, and as the ACKs come in for the segments you're sending, we increase that window size by the number of ACKs we've gotten. So yeah, you send one segment out when you first start up, right? You get one back. You get an ACK back. So now you send out two segments. And if those two get ACKed, now you're sending out four because you got two more ACKed. So 2 plus 2, you send out 4, you'll get 4 back, plus 4, 8. So you're starting with a tiny little amount, and then you're doubling it. Doubling. And you just keep doing this until you don't get one back. You don't get an ACK back. In which case, we switch over to the congestion avoidance algorithm. So this is slow start, where we're kind of just doubling as we get those ACKs back. But then once we don't get one back, we halve the window size and switch over to congestion avoidance, which is a sort of additive increase. This is where we're not doubling anymore. Each time a congestion window's worth of bytes is successfully transmitted, it adds another segment amount of bytes to the congestion window. So this allows one more potentially unacked byte out on the network, and you just keep doing that until you have to retransmit a packet because it didn't get ACKed, or because the server says you need to send it again. At which point the congestion window is like completely axed down to a really small level again, and we switch back over to slow start. So if this is like the threshold number magically where we're going to drop packets, slow start would have you going like, and then you, at some point you're over it, and you have from there, and then you're sort of linearly just adding one at a time until you hit it again, in which case you go way down, and then you start going up exponentially again. You know? No views, bro? Okay. I'm gonna go quickly weigh out how many of these chips I've already eaten to see if I can stop yet. All right. So that's slow start and congestion avoidance, which are our two congestion control algorithms that TCP uses to to deal with congestion control, which is alongside it dealing with flow control, ensuring the integrity and order of your data. There you go. Now, Beej puts a few questions at the end of each of his chapters. So we'll run through these. Name a few protocols that rely on TCP for data integrity. So this would be any application layer protocol where we are concerned about, oh yeah, I didn't even, this brings this up, but I sort of immediately got into like the spec of it, but the point of TCP is we care about all of our packets getting there in order, right? It's disastrous because of our application context or whatever. Like the data we're sending, it has to be as accurate as possible. We really, really, really want it to get there. We don't want to lose anything. It has to arrive in order. So what kind of applications or like scenarios do we really care about that versus other ones where it's okay to drop some packets? Well, you can think of like banking, or actually I think banking might actually use its own protocol, but that might be at the application layer. But yeah, if you are sending like wire transfers or something, like you really, actually I really don't. I should look this up. File transfer. This is a better example. You go to download a file from a server you want to download it to your computer. You really want to get the actual file from that server. You don't want any bit flips or rot or whatever. Like, if you go to download a ROM hack, you don't want it to just arrive on your machine completely like a puddle of garbage. It has to arrive and it's critical that every byte in that file gets to you the way it is on the server in storage or whatever. So the question, name a few protocols that rely on TCP for data integrity. HTTP, FTP, which is File Transfer Protocol, or SMTP, Simple Mail Transfer Protocol. So yeah, you send an email, you want your email to get to the right person with exactly what you wrote. It would be unacceptable for Gmail to induce typos, for say, into your email, or to not be able to guarantee your email gets there. When you send an email, you expect it to get sent. You know? Versus, we'll learn about UDP next, which offers sort of increased performance, but none of these features. You may very well lose packets. So where would that be acceptable? Video calling, streaming, certain aspects of like live gaming would be appropriate. If you're streaming a YouTube video and your client's like continually, like the server's continually sending stuff to your client, it's acceptable for some of those bytes to arrive a little out of order. You may not even discernibly notice any discernible change in your stream or stream quality, or there may be a little visual glitch, but it's one byte or like one little segment worth of this continuous stream. What's more important in that context is that you don't get buffering, right? And that you go to click play, and you generally speaking are able to just get through the whole thing, and be able to tell what's going on screen. So UDP is pretty good for that. So yeah, like video calling. Someone's voice goes a little weird, or the lighting gets weird, like there's some weird visual artifacts for a second just because there's some garbage bytes making it into the stream. That's fine. Right? But we wouldn't want to send emails over something like that with no guarantee it's going to get there. Why is there a three-way handshake to set up a connection? Why not just start streaming? So why is there a three-way handshake? We're simulating a what's it called? Circuit switched network on on what is actually a packet switched network. So we're kind of just triple checking that the sender and the receiver are on the same page, that one of them wants to send some stuff to like the sender wants to send stuff or get stuff from the receiver. So I want it. Yeah, I acknowledge you want it. I acknowledge you acknowledge me wanting it. Yeah, all right. All right, here it is. So what did I put? We're trying to simulate circuit switch. Yes. And the receiver knows the senders, and the receiver knows the senders know the receiver is ready to receive things. The sender can then rest assured their entire stream of segments will arrive to the receiver. Also for the initialization of, for sequence numbers. So we initialize the sequence numbers during this three-way handshake. So the sender and the receiver are on the same page about what the first number in the sequence numbers actually is. So this means, like, you could, as a server, have multiple sockets running, and right, like you're receiving several streams of data. You probably want to be receiving some of those on sort of like, you're getting segments 1, 2, 3, 4, 5 over here, but over here you're getting like 5,000, 5,001, 5,000, so that you can handle the whole ordering and stuff on both of those at the same, right? And that's because the sender and the receiver establish what that first number will be upon the handshake. How does a checksum protect against data corruption? I guess it doesn't. But what it does let you do is throw away the corrupted packet and ask for another one. But how to actually do it, it's what we discussed earlier. The client does its own checksum, puts it in its own header, sends it, receiver takes that checksum, sets it aside, computes the actual checksum on what it got, compares them. If they're the same, you're good. If not, you have to tell them to send it again, and you just drop whatever you were sent in the first place. What's the main difference in the goals of flow control and congestion control? Flow control is so that two devices can tell each other to slow it down. Congestion control is a pair of algorithms used to ensure that we're not flooding the network as a whole. And flow control is concerned with bytes. And I guess congestion control is more on terms of number of segments, but that could be wrong. Whatever the case, you can only send as many segments amounts of worth of bytes according to whether the congestion window or the flow control window is smaller, which is sort of heuristically like the worst one at the time. That's what you need to account for. Oh, I'm dying over here. The more of these you eat, the hotter it gets. The more you start sweating. Okay. Reflect on the reasons for switching between slow start and congestion avoidance. Oh boy. I just talked about this. You can rapidly increase, sort of optimistically, you're rapidly, exponentially increasing the amount of packets you're sending out until, whoops, okay, a little too much. So you cut it back by half, and then you sort of gradually increase it until you've overdone it again, in which case you go way back and start going exponential again. You go way down, start going exponential again. Right? Slow start, we're finding out the rough amount that we can get away with. Congestion avoidance is about actually getting you right up to that asymptote. Purpose of flow control is so that the receiver can tell the sender to slow down, so that the sender knows how many bytes it can send the receiver without exceeding the receiver's capacity to process that data and acknowledge its receipt. Allows us to operate on the assumption that most networks can tolerate sending a few seconds worth of data without explicitly acking each one as a predicate to sending the next. Allows the receiver to tell the sender that it can send X bytes. We went over all this. So, that's TCP. Let's talk about UDP. I guess I gave you a little bit of a teaser when I was talking about video streaming and what do you do if you don't care as much about the integrity and order and stuff. So, I need to sit down. Yeah. Sitting down made me a new man. Okay, so UDP, user datagram protocol. This provides us a way to send error-free data from one computer to another. Error asterisk. But it does not provide the data in order. It doesn't provide the data without loss. Doesn't provide handling like duplicates, and it doesn't offer any flow control or any of that. But since it doesn't offer any of these things, which in TCP corresponded to a field in the header or some bytes in the header, this means the header is much smaller. So each segment is like tiny.
like TCP, UDP uses addresses and ports to identify hosts. And once on that host, the OS uses the port in the UDP header to deliver the data to the application that is listening on that port. That's because we're not simulating like a circuit switch network anymore. And that's why people call UDP connectionless. You send a UDP datagram to an IP address and port, IP routes it there, and the receiving computer's OS sends it to the program bound to that port. That's not a persisting connection. It's just the transport of an individual packet. So the UDP header has its source and destination port right in it, which is everything the receiving operating system needs to forward that packet or that segment to. Are they called datagrams? I don't know. I'll call it packet, UDP packet. To whatever like application is listening on that receiving host on that port. It only does error detection, and in the same sort of way as TCP with the whole header checksum thing. Except it's obviously running that on the UDP header, not the TCP header. If the checksums match, the data is assumed to be error-free, and if they differ, the data is discarded, just like we saw with TCP. Now, UDP has this other thing we need to think about, which is fragmentation, and that's when a UDP packet ends up getting split across multiple IP packets when it's on the internet or the like IP layer below transport layer. This could happen because like the lower layers beneath transport layer decide to do this or not, depending on like the operating system or the route or whatever. So like this is just something that happens. So what do we do about that? Well, there's this thing called the MTU, maximum transmission unit. This is the biggest packet that can be sent on any particular wire, on any particular wire. And the biggest, so the MTU on IPv4 would be 576 bytes. On the biggest IP header possible is 60 bytes. A UDP header is 8 bytes. So that means we have 508 bytes of payload you can guarantee won't be fragmented. Or often 512 is used as the common segment because the IP header is often less than 60 bytes. So I think like the standard convention is like that 512 is the MTU for IPv4 UDP, So why do we care about fragmentation? Well, it's because many routers will just drop fragmented UDP packets altogether. So these routers, they don't want these big, huge packets, UDP packets. So what's the use? Well, if you don't care about a few packets getting lost, voice, video game, frame data, if you can't have packet loss, you can implement a protocol on top of UDP. So you can do all kinds of, I think TFTP is trivial file transfer protocol, I think, which is like UDP with some extra packet loss handling stuff built on top of it, that in the application layer, I think. So is that abstracting? That's abstracting away, or like demulti. See, it's tricky because you go down the stack, but if UDP is just the mechanism, the pure mechanism for just like the bytes getting to and from, you can write all the programs you want to try and reconcile any kind of packet loss stuff without relying on the actual transport layer itself, I think is the gist. There's a third reason to use it, which is if you want to multiplex different data streams without having multiple TCP connections. So to have multiple TCP connections, you'd have to have multiple sockets open. Each of them is listening on a certain address and port. But you can just tag UDP packets with an identifier so they all go to the right place upon arrival. Right? They have their source and destination address right in the header. Wait, I don't know. We haven't done anything with UDP actually yet, so I'll probably have better information on this. And the last reason you might use TCP or UDP is if early processing is possible, given the application you're writing. So if you really don't care about the ordering, or if there's something you can do with whatever you do receive before you necessarily receive the things that were sent in time before it. So if you can process packet number 4 before even receiving number 3 because of whatever your application is, then UDP is great for that. These have, so as far as like the Python like socket API is concerned, as opposed to using listen, connect, accept, send, or receive, because there's no connection with UDP, you call send to and receive from. So right here I just have a mock UDP server, which you now use the socket datagram type for when you spin up the socket. You bind to a port, and like while true, the data and the sender. So this is is received from and a certain number of bytes, as opposed to receive a certain number of bytes from just the open socket like you would with TCP, because there is no just open socket. You're receiving a particular. You're trying to receive a certain, or you're open to receiving a particular packet from a particular sender. Or from a sender. And then send a reply back to the original sender. So socket send to data.encode, which you send to a particular sender. Okay, yeah, that makes sense. And the UDP client you would be spinning up a UDP socket of type socket datagram for the, like, as opposed to the default one, and which resolves to TCP, or you can specify it with the socket. Yeah. And you use send to send a particular message to using a server port tuple, and you're waiting for a reply. Data center. So, what does TCP provide that UDP does not in terms of delivery guarantees? TCP provides guarantee that you get stuff in order, and there's handling for if you miss things. UDP does not give that. It has flow control and congestion control too. Why do people recommend keeping UDP packets small? To avoid fragmentation, which is when the IP layer or just routers just drop fragmented UDP packets or datagrams. A UDP datagram doesn't refer to a UDP segment. I'm pretty sure a datagram is the IP layer. So a UDP datagram would be a UDP segment wrapped in an IP header or prefixed by. Why is the UDP header so much smaller than the TCP header? Because you don't have the flow control window thing or the congestion control window thing or that like what else? What don't you have? What am I missing? It only has source port, destination port, the length, and the checksum. Whereas the TCP header has all those plus, oh yeah, the sequence number, the ACK number, the header length, the space for reserved bytes, the flags, which I think is that multiplexing thing from TCP, which we didn't actually talk about. The window size, the urgent pointer. No, that's what I'm talking. That's the where you can have a side or priority or whatever. Options and data, and yeah, okay. Send to requires you specify destination IP and port. Why does the TCP oriented send function not require those arguments? Because send to, the UDP doesn't have a connection, so send to has to specify where you're sending those bytes. Whereas we're not bound to an open socket. Right? The send function is used with connected sockets, meaning the destination IP and port are already established when the connection is made, so they do not need to be specified again. In contrast, send to is used with connectionless sockets, where the destination must be explicitly provided for each message sent. Why would people use UDP over TCP if it's relatively unreliable? Because you're living on the edge. Or because in exchange you're okay with faster and lighter weight segments that don't have any guarantee of flow control or congestion control. Because your application doesn't require every single packet to arrive in order. Okay, so that's TCP and UDP. Cool. And these chips are killing me. Alright, this is the coolest part of all this. But these chips are murdering me. I haven't had any water. Soon. Sooner I finish. Yeah, I'll be back shortly.
Okay. I'm back, sorry. I tried to like actually force feed a bag of chips. Ugh. Doesn't feel good, folks. So maybe with the light. The feelings disappear. You are someone else. I am still right here. Who I am. All right. Yeah, so validating the TCP packet. So for this project was to write the checksum algorithm. The checksum for a simulated TCP environment. So we were given a directory with 10 files in them. 5 of those, or 10 pairs of files. Gathering my thoughts. These are 10 test cases. 2 files each. One file is the source and destination IP, and the other file is the actual data. So we're simulating the TCP environment here. But we're actually just reading the source IP and the destination IP from a file, right? And then we're given the actual TCP data, which is like its header plus the data that the TCP header is a header of, so that we can compute its checksum and compare it to the checksum that is passed inside of it. So we're simulating that environment and just printing out for each test case what the checksum is for what was sent and what we received. The checksum sent and the checksum we computed based on what we received, and if those are equal, if it's a pass or a fail. And the first 5 we're told are a pass, and the second 5 we're told are a fail. So I think before I, like, you can kind of just go do this yourself. I learned a lot doing it, but I don't think it makes sense to like go through the whole spec, because unless you're like really sinking your teeth into this, you might not totally like get into it. So let me just swap over to my folder here where I work on this stuff, and actually maybe we'll go through it. So on the right I have my solution, and on the left I have the spec for the assignment. It gives us some general advice. So it's just so we read in the addresses file, split on the space, because that input file looks like 2 dot notation like addresses, like 192.168.10.5 and 192.168.10.11. So we need to get those and then convert those into byte strings. And that's because the source and destination addresses are actually used in the computation of the checksum. So we need to turn those into byte strings so we can like do the bytey stuff properly. And then we're told we should probably read in the actual TCP data, the header and body, right?
And then we have to generate the IP pseudo header bytes from the IP addresses from the addresses file and get the length of the TCP data. So more on that after, but the pseudo header is one of the components of what is the actual header, and we'll show how you do that. And then we concatenate and then we take the TCP header and we basically knock off the actual checksum bytes, which are the byte offsets 16 and 17. We just get rid of whatever the actual checksum passed in there is, just make that 0, but we keep everything else, and that's what we call the 0 checksum. So we use the 0 checksum and append it to the pseudo header. And it's that concatenation that we're gonna punch into our checksum math thing to get the actual like integer number that is the checksum. And then we're supposed to compare that with the actual checksum from the original data in the like TCP data. So yeah. So checksum in general. So what is a checksum? We talked about it broadly already, but in like hard facts here, it's the 16-bit value that represents the sum total of all the bytes in the packet plus a bit more. Oh, I thought this was going to say the actual ones complement thing. I guess that's later, so we'll get to there. So we already discussed all this stuff. Input file details. It's fine. So, how on earth do you compute a TCP checksum? Again, it's there to verify the integrity of several header, payload, and the source and destination. The last part is interesting. Aww. I'm telling my girlfriend to watch the stream. What have Oh, Ricky. Everyone I know. Goes away. You could my empire of dirt.
Eli.
Hey guys, say hi to the stream.
Hi, stream. On what?
On YouTube, bro.
Are you streaming what's nutrition content?
Yeah, the stream's called wait.
Play mid lane.
Explaining how TCP, UDP, and checksum algorithms work while eating a bag of chips.
Nice. Right. You're really getting down to brass tacks. How's it going, man? Silicone tax.
It's good. Anyways, I'm gonna get back to it, but
good luck.
Got,
have fun, bro.
Got Sadie in here, I think, first viewer. Alright, see ya.
Good luck, guys. See ya.
Okay. I just watched you pick your nose 3 times in a row. No. Are you in here?
All right. So where were we? So what's this whole IP pseudo header part? Well, it's actually pretty easy to put together. We need the source address and the destination address. And then here it says 0. This is literally 2 zeros. We're putting in a byte worth of zeros. And then PTCL, this is protocol. And there's like a specific like byte you put here based on which protocol you're computing the TCP header for, or the IP pseudo header for. And because we're doing TCP, that is 06 in this case. That's the TCPs. And then TCP length, this is just the length in bytes of the entire like TCP data file we're currently like working on calculating the pseudo header for. Yeah, 0x06. There's like cat hair in my nose. TCP length, total length. I will get into the example pseudo header when I show you my code. But like I just said, source IP and destination IP, these are each 4 bytes. 2 zeros, 2 bytes, or one byte for the protocol, and then the length of the thing, the TCP data. Getting the IP address bytes. So this is just a part. Okay, now it's just going to generally go through stuff. So I'm just going to go through my actual file. So the sort of main method solve here for I in range 10, this is just because we're looking at 10 files. So very specifically, dude, you have to go away. Get a job. So we open up the addresses file, and we take the source and destination, we can immediately get the source and destination if we just read that file and split on the space character, just because they're separated by a space. And we can convert each of those sort of dot notation IP addresses into byte form. No, you already drank my water. She already drank from this one. We can convert from dot notation to byte form by passing both of these into the convert IP to bytes helper. So we'll just skip up to that now. Very simple. You have an empty byte string, and you split on the period character and add each of those to an array. And for each number in that array, you just append to our byte string, our ongoing byte string, that number cast to an integer, converted to bytes, where we're representing each of those numbers with 1 byte in big endian form. And we just return the byte string. So source IP in bytes, dest IP in bytes, these are just 2 byte strings now that we can use for the pseudo header. So that's the addresses file we've opened and read and dealt with. Now we open the actual like TCP data file. This RB argument to the open method here is for reading a binary file, which this file is. Which lets us just read the entire file by calling read. So the file, its entire contents are stored in TCP data. What a freak.
Okay, it's time to wrap this stream up, y'all. So So we have the actual TCP file, or TCP data file read in, and we can get its length by just taking its length in bytes here. So now it's time to compute the pseudo header, which we call by just calling the generate pseudo header function, which I wrote up here. This takes a source, a source IP, a destination IP in bytes, a protocol in bytes, and length in bytes, and just concatenates them all together into a pseudo header. So that's literally just source plus dest plus or like the output is a byte string where you're adding the source IP, destination IP, then the 1 byte worth of zeros and then 1 byte for the protocol, which will be 06 when this is called, and the length in 2 bytes in big endian form. So now you have the pseudo header. Now step 3, we have to just figure out what is this original message's checksum, like what was actually put into the TCP header when the client sent it, and that's in bytes 16 and 17. So we just take that slice from the TCP data, and that's that. Step 4 is generating that 0 version of the checksum. So, like we discussed before, what we do is just take the entire TCP data and we just knock out bytes 16 and 17 and replace them with 0000. Like we're just right. It's like a TCP 0 checksum. So we just take the first slice up to the 16, and then on 16 and 17, those are now zeros, and we just put 18 onwards at the end of that. So now to do the actual checksum, what we first do here is if this 0 checksum thing we've done is odd, we just append a byte's worth of zeros to the end of it to make it even, like in length. Sorry, odd in length of bytes. So we're now guaranteed we're working with an evenly lengthed 0 checksum. And this is where we just implement like the pseudocode they gave us about how to do a checksum. So we've got this variable data, which is we concatenate the pseudo header with the 0 checksum. And we start with this offset of 0 and this like empty list of words. Words aren't like words, like as you think of them. These are 2 byte sequences. Yeah. So the offset starts at 0, and as long as it's less than the length of this concatenation of the 0 checksum and the pseudo header, you're taking and from bytes data at offset slice out 2 bytes and get their value. Okay, you're taking each set every 2 byte slices, and from byte form into integer, from big endian byte form to an integer, and you're just appending that to our list of words, and we increase the offset by 2. So yeah, we're taking every 2 and basically casting them from a big endian byte to a decimal like form, like integer. And once we've got all these words, like each of these 2 byte things, we're passing all those words into our
our checksum helper here, which is this helper. So what this does is you sum all the words in your array of words, and then this is summing all of the words with the ones wraparound. So we're summing a bunch of 16-bit numbers together. And if the sum of if that sum exceeds 16 bytes, we wrap the sum around to the first bit. And then we return the ones complement of that. So we are turning every 0 to a 1 and every 1 to a 0 in that number. And that's the checksum. You return that, and then if you print it with Python, it's going to print it as an integer, which we can then compare to the checksum that was passed by the client, or the client or the sender inside its TCP header. And we just print we print true if the one we just computed there is equal to the one that was passed in the OG one. And if you run it over here, you see true, 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 false, 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 true, 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 false, 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 false. The assignment told us that they have to be equal. My cat's making sounds I've never heard her make in her entire life. Like 3 different ones today. Freak. That's that assignment. That's the checksum assignment. How am I supposed to see my notes? IP routing. Okay, what do I do next? Dude, I did a lot. I'm not starting this now. This is all bitwise crap that I actually. Yeah, I'll do this tomorrow. Okay, so that's TCP, UDP, and checksum. I think we'll do bitwise stuff, which is used for IP subnets and stuff, later. I did IP routing. Oh, not even. So I got to routing tables here. Routing tables in chapter 18, which means I just have to cover chapter 17, the notes I took on it, which are here. And then we can continue on to the project for IP stuff. Well, it's been chill. Oh. Thanks for coming. Hope you learned something. Ciao.